Hello, I'm Terrence Neumann, co-author of the paper, Does AI-Assisted Fact-Checking Disproportionately Benefit Majority Groups Online? With Nicholas Wolczynski, a fellow PhD student at the University of Texas McCombs School of Business. First, I want to discuss our motivation for studying this topic. Mis- and disinformation continue to proliferate online. For instance, Facebook labeled 180 million posts as misinformation during the 2020 election. Some fact-checking organizations and platforms are using AI to assist in the fact-checking process. However, there are alarming trends related to mis- and disinformation slipping through the cracks in minority communities, potentially indicating a systemic deviation in access to high-quality information based on one's position in the broader social network. We aim to investigate whether this occurs and to what extent it can be alleviated by algorithmic design choices. As I mentioned, AI can be used to fact-check claims made on social networks. In general, there are two main algorithms used. First, algorithms are used to assess trending claims made on a social network, helping fact-checkers prioritize which claims should be fact-checked. Second, an algorithm is used to identify previously fact-checked misinformation that continues to be posted on the social network, taking some content moderation action like blocking or warning users. In our research, we focus on design choices related to the first algorithm, called check-worthiness estimation. Check-worthiness estimation is a somewhat nebulous concept. It has a variety of definitions put forth by different researchers and practitioners. It is often operationalized as whether a claim may harm the general public if left unverified, while others have thought that it pertains to the harm to a specific group or individual. Practically, a check-worthy model takes a claim and relevant metadata as input and produces a categorical or numeric prediction that indicates how check-worthy a claim is. Previous approaches to simulating information sharing behaviors online include the susceptible, infected, and recovered models, which are adapted from the epidemiology literature, and other bespoke agent-based models that incorporate probabilistic information sharing behaviors. However, from our analysis of the existing literature, no theoretical models accounted for the fact that various online communities may be differently impacted by and have differing beliefs about certain topics of information. In response to this gap, we developed the topic-aware community-impacted Twitter simulator, which we call TACIT for short. This model incorporates some basic assumptions about node behavior. First, it assumes that agents in the network have bounds on their rationality, meaning that they don't have access to all information in the network and that they have a limited memory. Second, we assume that online communities in the network have aligned interests, and that communities will be differently impacted by certain topics of information. Third, we assume that online communities have differing beliefs about certain topics, with some communities possessing ground truth knowledge and others assuming misinformation to be true. Finally, we assume that there exists a small community of experts who consistently have high ground truth knowledge about an array of topics, such as journalists or scientists. Given these assumptions, TACIT simulates a microblogging platform with information sharing options similar to Twitter. TACIT takes as input a community-segmented network. Communities can either be ground truth or detected from an algorithm using a measure like modularity. When sharing information, nodes tend to tweet about topics that they are impacted by. And based on assumption 2 from the previous slide, nodes within a community are impacted by similar topics. Second, nodes read tweets from other nodes that they follow and potentially further propagate this information. Whether they propagate a tweet is probabilistic, and it's dependent upon their beliefs, their impactedness by the tweet, and the popularity of the node that shared the original tweet. Additionally, nodes have a set of information consumption behaviors that feed the dynamic nature of the simulation. Nodes read tweets from those that they follow. These tweets then update their beliefs. If they read largely misinformation, they begin to produce and retweet more misinformation. If they read largely anti-misinformation, they begin to produce and retweet more anti-misinformation. If they read noise, this doesn't change their beliefs. We use the TACIT simulator as a testbed to generate realistic data propagation patterns that can be used to train a check-worthiness algorithm. Recall that we are investigating how design choices of check-worthiness algorithms impact the distribution of benefits from AI-assisted fact-checking. Using a framework for assessing diversity in socio-technical systems from Faisalpour and Diartiaga, we investigate 3 independent variables in the design process. First, who is represented in the training data? Second, whose views and knowledge are encoded in the algorithm? And third, who is included, benefited, or harmed by the use of the algorithm? Returning to our AI-assisted fact-checking workflow, we operationalize these variables in the following ways. First, we vary how claims are sampled from across the network. As a base case method, we look at the most viral claims across the network, which will likely overrepresent the majority community in the training data. As an alternative method, we sample the top N most viral claims in each community for our training data. Second, we vary who encodes the labels used to train the algorithm. As a base case, we take a random sample of labels for claims from across the network. We test 2 alternative methods. One is a community stratified approach in which there is an equal representation amongst communities in data labeling. The second is a knowledgeable community approach in which only the community with consistent ground truth knowledge about a topic is used for acquiring data labels. Finally, we vary how fact checkers use these predictions. As a base case, we assume that fact checkers simply use the predictions to rank order the claims for fact checking, checking the top N rated claims per time step. As an alternative approach, we assume that fact checkers stratify their workflow by topic. For instance, if there were 2 topics in the universe, fact checkers would check the top N over 2 rated claims for topic 1 and the top N over 2 rated claims for topic 2 per time step. Finally, we assume that algorithm 2, the algorithm that identifies previously fact-checked information, is 100% accurate and always blocks information that has previously been fact-checked from being tweeted or retweeted. In order to assess the distribution of benefits from the different algorithms, we measure the change in belief of each node throughout the course of a simulation. If we see a positive change in belief, this indicates that a node lost ground truth knowledge overall due to a high consumption of misinformation. A negative change in belief indicates that the node gained ground truth knowledge thanks to decreasing consumption of misinformation. Because we are in a simulation, we can observe every node in a state both with and without an AI-assisted fact-checking intervention. Therefore, we can precisely estimate the treatment effect of the fact-checking intervention on the node, which we can average over all nodes within a community to get community-level average treatment effects, which is essentially the distribution of benefits from AI-assisted fact-checking. We run these experiments with a majority and minority community that are equally unknowledgeable about topics but are impacted by different topics. We also include a small expert community that is equally impacted by topics but is also very knowledgeable about the ground truth of the topics. We repeat this experiment on a Twitter followers network dataset 10 times and report the results in the following sections. In this chart, we see the average treatment effect across communities in our experiment. The green bar represents the treatment effect of the minority community, the blue bar represents the treatment effect for the network as a whole, and the red bar represents the treatment effect for the majority community. First, we find that an egalitarian method across communities for sampling training instances provides significantly more benefit to the network than through a representative method for sampling training instances. However, almost all of the benefit is concentrated in the majority group, indicating that this method, while good for the overall network, could exacerbate inequalities in high-quality information across online communities. Second, we find that using labels exclusively from knowledgeable communities provides a significant benefit for both minority and majority communities compared to random sampling and community stratified sampling. While the majority community does benefit more than the minority community, both communities see a nearly 3 times improvement in average treatment effect when switching from random label sampling to knowledgeable community label sampling. This highlights the importance of using experts in the check-worthiness pipeline. Finally, we see that fact checkers can actively reduce disparities by stratifying their workflow across different topics. When they actively stratify their workflow by topic, they reduce the benefit to the majority group and increase the benefit of the minority group. However, it is worth noting that this means that the average node becomes worse off in the network, meaning careful consideration is necessary before implementing this intervention. Thanks for listening to our presentation. I hope you enjoyed our talk and feel free to reach out if you have any questions.